Right, let's get started with our last two talks of the day. End of the workshop.
Okay, the second speaker is arriving, so we can start.
Maybe delay you to 2 hour lunchtime.
Okay.
So, Alexei from Collège giving us our talk, second to last talk. Of course, the speaker.
Hi, everyone. First of all, I'd like to thank the organizers for inviting me here. It's an awesome workshop. Thanks, everyone. So that's us. If you watched last year's Olympics, you roughly know where we are. Geographically speaking, we're still at Collège de France now. Socially speaking, we're pretty much now at LKD. That's the big quantum physics lab that people know. And eventually, we're supposed to move there as soon as the physics building where Romain and Jacob work stops looking like it's been hit by a missile. So I'll start by showing you a picture that you've seen already, I think, twice this week and 2,000 times before. This is the quantum internet by Jeff Kimball, where the idea is to connect static qubits, which I will call atoms with quotes, using flying qubits, which are usually photons. And because they don't interact very strongly, we tend to put these atoms in cavities. Now, the canonical way of interfacing these things is to take a 3-level atom, and if your photon comes in, you gently ramp down this control laser, which essentially adiabatically rotates this dark state. So you rotate your single photon into an atomic excitation in that storage state down there. And then you can reverse that process back and forth and spit your photons in and out in a essentially coherent way. And there's been a lot of work on that by many people, for example, Gerhard Heimpe. So that's ideally, in real life, nothing's ideal. So you have atomic decays, you have scratches on mirrors and various annoyances. And then at the end of the day, these experiments are essentially, as all of our experiments, going to be limited by the cooperativity, which we've seen 2,000 times this week, which you can rewrite as the product of the finesse times the scattering cross-section of the atom versus the essentially cross-section of the photon, the waist square. But in this type of experiments, you also need to maximize the cavity extraction efficiency. So that's what's the efficiency with which you can extract a photon from the cavity. And that's the ratio of the useful transmission over the total transmission. So you cannot make that transmission that low. So that's an additional nuisance. The usual way people tackle this problem is to try to make the photon as small as possible by confining it in a small volume cavity. But you can also make the atom larger. So the whole historical way that people did that, it was just by increasing lambda, so that going to microwaves, so that were the experiments of Serge Haroche in particular. That's why they work so well. What we do is slightly different. We still work in optics, so we cannot do anything with lambda. We instead increase the number of atoms. Instead of putting 1 atom in there, we put n atoms and about 1,000, and that automatically increases the scattering cross-section by a factor of n. So the cooperativity goes up by n as well. And of course, the system becomes linear in that case. So to turn it back into a 2-level system or a 3-level system, we, instead of coupling this intermediate state where we now have a delocalized excitation instead of a single excitation in this so-called symmetric decay state, we take this state from here and we take it up and we laser couple this guy to a Rydberg state. So now we have our qubit encoded in a ground state or in a delocalized Rydberg excitation. And this works because now we have Rydberg blockade, which in a range comparable with the size of our clouds can ensure that we can have only 1 excitation and not more. That's the ideal theory. So that's what we set up in the lab in the last few years. The way it looks like, it's a procedure like a magneto-optical trap, then transport to prepare about 1,000 atoms in a small cloud with a Gaussian radius about 5 microns and a reasonably cold temperature. We can drive into Rydberg states that are pretty high. The 109S is our typical workhorse. So the Rydberg blockade in that range is about 20 microns. So that looks much bigger than this, and I will tell you why this is not the right things to look at. And so despite all the experimental misery, including a 100-volt piezo blocking the cavity length, we have Rydberg line with about 50 to 80 kilohertz. So we've done some effort in shielding on that. The cavity itself, it's a 4-mirror cavity, looking very much like John's, for much more mundane reasons, like having modes more or less like our Gaussian and the polarization right. We didn't have all the crazy Laughlin states there. It's 2 small mirrors, 1/4 inch on one side, 2 on the other. The distance here is about 2 centimeters. The finesse is moderate. The mirrors are actually quite bad. We're gonna have to change them at some point. It's a single-ended cavity, so this guy transmits about 1%, and the 3 other mirrors are HR. Depending on how many atoms we load, we typically work with collective cooperativities in the 10 to 20 megahertz, so that's to be compared with the gamma of the intermediate state and the kappa of the cavity, which are both about 3. And this photon extraction efficiency is reasonable. It's 90%. It used to be 95 before we baked the system, and then drop down and it stays there. So it stays. As mentioned several times, Rydbergs are pretty fragile beasts. So you need to have a careful control of your electric and magnetic fields. So this is these copper electrodes around. And these states 109 are pretty high lying, so they're not trivial to excite. And for this, we added 2 other cavities. So that starts entering the theme of this workshop. So we have 3 in vacuum cavities that are crossed in the system. And these build-up cavities, well, in order for everything to stay aligned after putting the things in vacuum and baking them to 130 degrees Celsius and then cooling them down, what we did was to do 2 confocal cavities so that the axis of the cavity is on purpose slightly below, like about 0.5 millimeter below the cloud. And then you can hit your confocal cavity off axis and align from the outside of your vacuum chamber on the atoms. So that gives us a decent power for these lasers, about 4 to 5 watts running in. And so the finesse of these cavities was also adjusted so that we can switch them on and off reasonably quickly. Now the point of using these superatoms instead of single atoms is that you can have cavities with funny geometries, and in particular, 2 of these mirrors, we can move them back and forth so that we can change independently the FSR to tune to different transitions, or the transverse mode splitting to go from single mode to multi-mode experiments. We have in vacuum the couple of high resolution lenses to make these small clouds with about 2 micron resolution so far. And because it's a quantum optics experiment, and at the end of each experimental run, you have like a couple of photon clicks and not an image of a DC, you need to make sure that your experiment runs reasonably fast. So put some effort in the rep rate. So what we've done so far is, of course, all the usual like ABCD grammar of qubits. First of all, do Rabi flopping, so single qubit gates. You prepare your atom in the ground state, and then you off-resonantly drive them from this state and back and forth to this Rydberg state, and you see this Rabi flopping. I'll get back to that later in the talk. We learned how to detect them. So for this, so our qubit is either here or here. And then we shine this auxiliary EIT probe laser on that transition. So if the qubit is here, we see Rydberg EIT, so the photon. So this guy makes the cloud transparent, and we have some finite photon flux. And if the qubit is out there, we chose these states on purpose to be first resonant, so that the transmission is very low, up to 40 microseconds here when it jumps up, because the qubit decays down to the ground state and we recover that transmission again. And for this, we can just integrate this photons flux over about 10 microseconds, and then say that if you have fewer than 5 photons, it's in a Rydberg state, otherwise in the ground state. And that gives us a detection efficiency of 95%, which is a lot worse than 99 something that we've seen previously, but it's kind of okay for a first shot. Now, one of the key things that we've put in the design was that we've chose the parameters of our mirrors and of the cavity, so that if the superatom is in G And if we shine light in here, it's essentially transparent. So the losses in here are much smaller than the input-output coupling transmission of 1%. And then the light enters the cavity, resonates in there, and goes out with a phase 0. And we can measure that with the homodyne detector. And if the superatom is in Rydberg state, the losses become much higher than the 1% transmission. And the light again bounces off the cavity, but now with the phase pi. You can use that to measure the state of the superatom, and that works about the same way as, and with the same efficiency as the photon count and transmission measurement. You can also use that to do cool stuff to entangle the state of the optical pulses that bounce off the system with the state of the superatom. So that's on our to-do list for the next couple of years. What we've done so far in terms of quantum optics was to prepare a superposition of ground and delocalized Rydberg states for this superatomic qubit, and then coherently convert it using, again, this dark state that I mentioned at the beginning of the talk into a superposition of ground of 0 and 1 photons. And because the system is optically efficient, it's emitted out of the cavity, and we can actually, well, first of all, detect them with about a 60% efficiency, which is kind of good for quantum optics. We can, of course, verify that's single photons and not more. We had a G2 of 2.7% back then. Now it's 1% actually, because we have some laser leakage back in the days. And we could send them to a homodyne detector and make a complete homodyne tomography for different qubit rotation angles. So when the qubit is weakly rotated, you see this kind of a bean-shaped thing that's slightly squeezed in that direction. And then it evolves into a negative Wigner function, which people in quantum optics are kind of excited about because it's cool stuff to do with this. And this is kind of the first time people did that completely deterministically. While doing that, so this is where the physics, I started learning physics by accident. Like, I know you, but me, when I was an undergrad, I was told that if you have a qubit, your qubit has two characteristic times. It has a T1, a lifetime, and a T2. That's the dephasing time. And if you want to measure them, you do Ramsey spectroscopy. You put your qubit in a superposition of states, you wait, another pi/2 pulse, you measure, and you see what happens. And I lived with that for 20 years or so. And I thought that was the only way. It turns out that you can get the same information, the T1 and the T2 of your qubit, by looking at the quantum statistics of the light that it emits, and not just by looking at the squeezing of the light that it emits. The squeezing does not behave the same way under the effect of losses and of dephasing. Hand wavelengthly, you take a Gaussian vacuum, you squeeze it, and then look like this. And then decay is going to turn it back into a Gaussian vacuum, but there's always some squeezing left. Now, dephasing is going to do this. And that's going to pollute the squeeze quadrature with the anti-squeeze one. So it's not the same effect. And you can just fit your data and extract these two parameters independently. Of course, it only works when your qubit is, when you can efficiently detect the squeeze light that's emitted by your atom. If you just have an atom in free space, that's not the smart way of doing this. But in our case, it works. And it's comparable with the Ramsey spectroscopy, I would say. And then, so for, I would say, the rest of this talk, I'll spend some time trying to explain you in what respect these superatoms are different from single atoms. And I'm an experimentalist, and I very much like things to be simple. Now, this guy on the left is quite obviously simpler than this guy on the right. And there must be some price to pay for that. You win, of course, by using superatoms because you have a higher cooperativity and you can relax tons of things on your cavities, but you must lose somewhere. So where do we lose? The first point, I tend to call that the revenge of quantum dots. Now, I know if people working here with solid-state emitters or people have friends doing solid-state emitters, they always get upset about atomic physicists because atomic physicists get on the nerves saying, oh, our qubits are all identical, your qubits are all different. I know I have people working with like NV centers and they don't like me for this. So these superatoms are in a sense, identical because they have the same resonance frequencies, unlike, say, quantum dots or these kind of things. But they don't have all the same dipoles. This dipole that they have, it's a collective dipole that's multiplied by square root of n for this collective radio frequency. And because I don't count exactly 800 atoms each time I load my trap, I have Poissonian fluctuations. So when I think I did apply pulse, sometimes I undershoot, sometimes I overshoot. It's a known problem. People have worked on that for years. You can try to measure your coupling. You can try to count the atoms. I think Dan's done some work on that in the past. I'm not mistaken. We haven't worked in that direction yet. The second problem, so your qubits have to be identical. These are a bit less identical than those. Your qubits have to be enharmonic. For a single atom, it's easy. It has very enharmonic structure. For superatoms, your enharmonicity comes from Rydberg blockade. So what happens if your blockade is not perfect? That's a very rich subject. I'm not going to say too much about that. But for example, you may ask yourself, why do you need a cavity at all? I mean, why don't you just put more atoms in your superatom and decrease your cavity finesse until it reaches 1? And you no longer have a cavity in vacuum and you save all the hassle. That's actually where this field started. Back in the days, so 15 to 20-ish years ago, from first experiments from Stuart Adams's group, and then many other people, John here and Vladon and many others. The issue is that in order to do that, you need to put quite a lot of atoms inside the blockade sphere to have a high optical depth. If you put in numbers, it's actually not insane, it's feasible. So people start doing that, in particular with BECs, because BECs are awesome, they're dense, they're cold, it just looks like it's perfect for these experiments. And not only their experiments didn't work better, but they actually started working worse, not working at all. And what actually happened is that when you start increasing the number of atoms inside the blockade volume, you end up putting atoms inside the Rydberg atom. So you have an atom inside an atom, which is kind of a conceptually cool thing. But these Rydberg atoms themselves, they're big. Their wave functions are about 1 micron. And as soon as you have more than 1 atom per cubic micron, which happens quite quickly, these kind of things occur. And then you start having collisions between this Rydberg electron and the surrounding gas. You get super cool cold chemistry. And Gilman Favre's been working on that for many years now. But for quantum optics, it's a kind of a showstopper. Now, again, I promised I'm not going to spend too much on Rydberg physics. I just want to show you that these superatoms, I mentioned quantum dots before, and you can ask yourself, are these superatoms closer to single atoms, or where we can model things like from first principles? Or are they closer to quantum dots where you need to put some numbers on your data? It's actually closer to single atoms. So the way we model imperfect blockade in our case, and the effect of imperfect blockade, where by accident, because the blockade is not perfect, I can have 2 excitations instead of 1, is this rapid dephasing, which is going to depend on the distance between the atoms because they have van der Waals interactions typically. We can do that in a very simple, effective model that I almost finished writing and should be online before the end of the year, where we decompose these special excitations in the cloud on a very nice, mathematically nice basis, just the eigenstates of the harmonic oscillator. And then we take a few of them, treat the rest as a broad continuum, use the resolvent formalism, and basically we have a model where with a few states, we match perfectly brute force numerics where we load it, where we simulate a cloud of like 400 atoms in a Gaussian trap, even in the case when the blockade is visibly very bad and when the evolution is visibly non-exponential and non-Markovian. And it also works reasonably well with the experimental data for the states that we can access. Of course, the stronger the blockade, the better the fits. But this is essentially no free parameter interpolation. Now, the last Oh, sorry. One thing. I told you when I showed my setup that my rear blockade was about 20 microns, and my cloud's Gaussian radius is 5 microns. And you may conclude that we are in a super strongly blockaded regime. If you try to make an order of magnitude estimation, you take the C6 coefficient of the states that we use, and you divide that by the Gaussian radius to the 6, you get interaction energies in the order of 10 gigahertz. And this is completely irrelevant to us. It's 4 orders of magnitude higher than what we actually see. It's not a factor of 2, it's not a factor of pi, it's like 10,000. So how the hell can you lose a factor of 10,000 in an order of magnitude estimation? The answer is very simple and disappointing. It has to do with caveats of dimensional analysis. Dimensional analysis says that the interaction should go as C6 over a characteristic length. So what's this characteristic length? It could make sense that to assume that the first excitation is somewhere in the middle and the other one is somewhere around here, but it obviously doesn't work. You can try to choose the most likely distance between the atoms, and that's actually going to be the diameter. So it's 2 sigma. That gives you a factor of 64, but it's not 10,000. What actually has to be used to get the right numbers is the peak of the state density. So you excite 2 atoms at random, you calculate the energy, and then you make a histogram. And you can calculate that analytically. It's very simple. And the peak of that density is actually very low. It corresponds to an effective distance of this equal to this Gaussian sigma times 3√4. 3√4 is 4.5. So dimensional analysis here works because it's of order 1. But if you take 3√2 to the power 6, that gives you 10,000. So this is actually the right size of your cloud that you have to take into consideration. And 5 microns times this is actually slightly bigger than 20 microns. So we're not that well blockaded. Last but not least, inhomogeneous dephasing. As mentioned before, the qubit that I manipulate is all the atoms in a ground state or one excitation in a symmetric decay state. Because my atoms are cold but not too cold, they move left and right. And then they accumulate different phases depending on their velocity, so just top-up shifts. And this symmetric decay state is coupled to an almost infinite bath or almost quasi-continuum of these asymmetric or dark or subbrahnian decay states, whatever you prefer to call them. I thought that this was the most boring and well-studied problem ever because you just have to cool your atoms more. Or you have to use motion insensitive schemes, or et cetera, et cetera. I mean, there's decades of work on that. The only reason I spent any time on this was that my students asked me to. And my students asked me that for the following reason. We started modeling our experiment, trying to understand how it works. How should we turn on knobs to make it work better? And then the natural idea, of course, when you try to model this, is to include that in your master equation and add some last term, which, well, it could be, for example, the velocity of the atoms over the wavelength that gives you a typical decay rate. If you do that, if you just put that in a normal Lindblad master equation, that tells you immediately that this decay should be exponential. And it's not. It's clearly not. I mean, you cannot fit a nice exponential over this. It's not super surprising. People in quantum memories know that quite a lot. This is a Gaussian because we have a Gaussian cloud. They have a Gaussian Maxwell-Boltzmann velocity distribution. And this curve is essentially the Fourier transform of a Gaussian, which is, again, a Gaussian. That's boring. Except that it doesn't help you that much. People in quantum memories, like Julien Laura, next door and others, they're kind of happy with just stopping there because they know exactly when they created their excitation in the cloud. In our case, we're using these crazy shaped pulses, and we now have 2 superatoms in the cavity, and it's all dynamical. So I don't have a t equals 0 to start this Gaussian somewhere. So the very low-level, simple question that we ask ourselves, how to model these dynamics, which are clearly non-Markovian, you can have there's a lot of literature on non-Markovian open quantum systems. Nothing of it was super user-friendly at my modest experimental level, back then at least. So what we did was to realize that you can actually map this dephasing process into a displacement in time frequency phase space. So there is such a thing. It's not just my imagination. People do that. You take your Hamiltonian where these x's are like individual Doppler shifts normalized by the typical width of that spectrum. And you take a continuous limit where you say basically I have many atoms. And that maps on an operator which just looks like a position operator X for a particle, say 1D motion. Then you start from your symmetric state and you build one by one the asymmetric ones by coupling the symmetric state, which has to satisfy these constraints. So the square of its wave function has to match your spectrum. And then you apply your Hamiltonian once and then twice and then 3 times to build your ladder. Now your Hamiltonian is just X. So you're taking this function, whatever it is, and you multiply that by X and X squared and X cubed. So at the end of the day, you're going to be looking for a family of polynomials that are going to be orthogonal under this weight function. And that's an easy mathematical problem, like even for experimentalists like me. So you get a Hamiltonian that's going to be tridiagonal. It only has this diagonal and these terms in the first upper and lower diagonals. And either this process stops by itself at some point, it can, or if not, you calculate a few of these states to act as your memory for your non-Markovian process. And then you say, okay, that's enough to model my system accurately. I stop at some point. And then I consider that everything that's above is a memoryless broad continuum. And you model that, so the coupling to that continuum gives you a lamp shift and a decay rate. And you can use the resolvent, it's basically something like a green function if you don't know what that is. And that gives you in exactly 3 lines of calculation these recurrence relations that allow you to calculate these lamp shifts and decay rates instantaneously. So just as an example, let's consider Doppler broadening. So my atoms are hot, they move left and right, they have this Gaussian spectrum. So the square root of a Gaussian is a Gaussian. And unsurprisingly, when you start constructing your states, when your fundamental state is a Gaussian, this is the fundamental state of a harmonic oscillator, you end up with Hermite-Gauss polynomials. So you build your Fock states that are going to be coupled with the square root of K Hamiltonian. And the decay rate you calculate, you actually can get it exactly, doesn't even look that ugly. And if you put a few of these states in your model, you actually realize that you describe your Gaussian decay much better than just by an exponential. My colleague Sébastien, so it's the same Sébastien whose name you've seen many times yesterday in Jakob's talk. Now he's in my team. He's a staff senior scientist. Came up with an example where he thought we could not calculate things analytically. That's atoms put in a dipole trap and seeing different light shifts. The spectrum, I mean, the fundamental state looks kind of ugly, but still you can essentially calculate everything analytically, even in that ugly case. So this is, I could stop here and say, okay, look, I hope I convinced you that these superatoms are more like atoms than quantum does, because we can model them from first principles. And that's what I basically started writing down at some point in the paper. And I just, in the course of, I don't know what took me, but I decided to make a sanity check. Does this model reproduce my intuitions of what would happen when I start driving this qubit with a constant radio frequency? So I take my qubit, I start driving it between the ground state and Rydberg and this symmetric state, and I see what happens. Omega is constant, nothing special. What my intuition was dictated by what I knew already from standard qubits. If you take a standard qubit, there's an atom that can decay somewhere else, and you start driving it. So this decay process is going to be described by a Lorentzian spectrum, and it's going to be Markovian by definition. Then you realize that if you drive it strongly, when your omega is 10 in units of this line width, or anything above, your qubit oscillates, and its effective decay rate becomes 2 times smaller than what happens with that if you don't drive it at all. It's kind of simple. It just spends half of the time in the ground state where nothing happens and half of the time in the upper state when it decays. So it's nothing magic. And you can drive it as hard as you want. It's always going to be this factor of 2. So I thought I would find something, maybe not 2, maybe I'll find pi, maybe something. Because I did not at that moment, maybe I was just stupid. And this, by the way, comes also out from standard block equations. So you can do that. You can make your undergrads do that. Now I thought I would find something similar with a different factor. Maybe I didn't quite expect to see this. So for the same Doppler spectrum and the same parameters, your qubit oscillates forever. So after searching for errors in my code for a couple of hours, I realized that actually I knew what that was. And I sat down a bit more with pen and pencil and actually verified that in a limit where this driving is really strong, your decay becomes exponential and no longer Gaussian. And that the constant that you have in the exponential decays itself exponentially with the driving strength, with the driving intensity. So it vanishes very, very fast. You also have that to a lesser extent for the light shift, where this constant vanishes, but now with the field and not with the intensity. And what happens here, actually, if you look closely, this converges to 25% because I have essentially a bit node between something that vanishes with this constant and something that doesn't seem to vanish at all. So that got me curious. And let me give a hand-waving explanation for what it's worth of what happens. We start driving this qubit. In a couple bases, we have these 2 eigenstates, psi plus, pi minus, g plus or minus r over root 2. Okay? Now, if you remember your undergrad classes about open quantum systems, to consider that your system decays in a Markovian memory-less process, you have to verify that the coupling constant between your quantum system and your continuum does not depend on the frequency. It's coupled to a broad continuum with a constant that's the same everywhere. What happens for a Markovian process? So a Markovian process has a Lorentzian spectrum. So my fundamental state, which I can take the square root of a Laurentian, but I can also add a phase there, so it can look like this. And my coupling constant consists in taking this fundamental state, so it's going to act on the R part, multiplying it by X. This is my coupling Hamiltonian, and that goes somewhere in the continuum. So it looks like this, and this is essentially flat. So no matter how strongly I drive my states, no matter how strongly they're split, they're always going to decay somewhere. For a Doppler spectrum, this constant it is very localized around 0. So as soon as I start driving them strongly, this decay is suppressed. For the light shift, this guy is asymmetric. So the upper state decays in the tail of that thing, and the lower guy has nowhere to go. Of course, I told that to my students over lunch, and it was at that point a very easy experiment. So they came back in the afternoon with essentially these curves. It works. We've tested it 2 things. We've tested a pure Doppler spectrum by making our atoms slightly warmer than we could. And we tested the spectrum by making them cold as we could, and adding a light shift, so keeping the dipole channel. We've arranged the parameters so that when we just prepared them and weighted, we had a decay constant that was roughly the same in both cases, 2.6 microseconds. And then we started driving Rabi oscillations and saw that we could drive them for much longer than this natural decay. Of course, there's no free lunch, as usual, I mean, except at Stanford. And at some point, things break down because you're limited by the quality of your Rydberg blockade. If you drive too hard, you start adding multiple excitations. Very important slide on which I could actually probably stop at the end. Am I trying to cheat you and sell you something that you already have and you already know? Is it something as stupid as spin echo or spin locking that you've studied as undergrads? So spin echo, I know what, I mean, you know what it is. You take a qubit, you made an error on the resonance frequency because it has maybe a Doppler shift or something. And you wait for a while, you flip the ground excited states, you wait for the same time, and the phase factors out. Of course, we can do that on many qubits in parallel, because why not? And it's not the same thing. It's not the same thing for 3 reasons. First of all, for this to work, you can make this dynamical decoupling, or you can just keep this laser on all the time. That's called spin locking. But in both cases, the radio frequencies of your laser in that case have to be bigger than any of these small shifts. In our case, it's only true for the collective radio frequency. The collective radio frequency has to be bigger than the width of the spectrum, but it's not the case for the individual ones. It's actually not the case in practice. The second reason is that this spin echo or spin locking process intimately relies on the swapping of ground state and excited state populations. We cannot do that because we have Rydberg blockade. I cannot put 999 Rydberg atoms in my cloud. And finally, and crucially, this process that I've shown crucially depends on the shape of the spectrum and not this guy. So it's not spin locking, but it's something that you know. It's cavity protection. It's the same thing that James mentioned in his talk. It's the same thing that people saw in different systems that's been studied theoretically nicely by the groups of Alexei and Klaus Mollenberg a few years. And that's in this room been studied a couple of years ago by Jacob and Romain on one hand, and by Jean-Philippe on the other. It's exactly the same process where you put an inhomogeneous ensemble of emitters in a cavity, and when your collective coupling becomes strong, your emitters essentially narrow down and you see only the natural line. It's the same thing because it's exactly the same equations up to a change of this collective coupling to a collective coupling to a laser. It's maybe a bit more mundane because instead of coupling to the vacuum mode of a cavity, you're coupling to a bright laser on one hand. But on the other hand, it's kind of, on a practical side, it's kind of cool because you can do things with a laser that you cannot do with a cavity, like switching it on and off or changing the phase. So you can, for example, what I'd like to do is make a pi over 2 rotation around this axis and then change the phase of my laser to lock my superposition states and see how long I can keep them and so on and so forth. So cavities are everywhere. Last slide, I'm done. Ongoing work now, we have 2 superatoms in the cavity. I'm not gonna develop on this. We've started playing with them, loading them, controlling them. We've of course bumped in the problem of how to detect one without having the other blocking the view. And we apparently found the same solution as Ziv. If you look at this level scheme, you realize that it's the same thing as what he's shown, but we have this lambda level scheme. And of course, we kind of thought and looked at this thing as using EAT to make the second cloud transparent rather than just shelving. But it's essentially the same scheme. And we've been playing a lot with a controlled coherent photon exchange between the 2 superatoms where we can prepare the first superatom in some given superposition state and then coherently transfer that excitation to the second superatom via the cavity and see that the phase of the film that leaks out at the end of this whole process is still coherent. With this, I'm not gonna retain you any further and ask for questions.
So this confocal buildup cavity idea is super cool. I guess I'm wondering how far you can actually displace the beam in the buildup cavity before astigmatism like breaks the degeneracy. And do you see effects of backscattering in the cavity or other stuff, or it just works properly?
Okay, great question. As usual, there is no free lunch. So in the current setup, one of our cavity works better than the other. The reason is that for a confocal cavity to work well, you need 2 things. You need to have the cavity length equal to the radii of curvature, and you need these 2 radii of curvature to be the same. And if you put in numbers, they have to be the same by much better than the tolerance of the mirrors that you just buy. So we've selected 2 mirrors for one cavity that work better than for the other. So you need to have a batch of them. So the cavities in our cases are about 15 centimeters long, and we had to adjust the length to about 20 microns to make that reasonably confocal. Of course, what's reasonably confocal depends on the finesse. And I purposefully had a finesse that was not too high because of that, and because I wanted to switch my blue lasers on and off within a few hundred nanoseconds. Backscattering so far is kind of okay, but the finesse of these cavities has been degrading for the same reasons that everybody has, and nobody really can. Well, we'll try your trick with oxygen at some point. Probably.
But how much can you move the beam on the mirror?
So the design is to be off axis by 0.5 millimeter. When I tested them out of vacuum, I could go to about 1 millimeter, I think, before the peak really broadened.
I have one more, actually. So it seems like in these Rydberg EIT experiments, people tend to bottom out in terms of gamma Rydberg, like this collectively suppressed line width or whatever it is, around 50 to 80 kilohertz. Do you have a sense of what's limiting you there?
I think in our case, it's mostly stray electric fields because of stuff around. If you talk to Sebastian Hofelbert now, he's down to 10, I think. So it's pretty neat and clean, but that's because he has less stuff around his atoms, and he's using the same states. It's like 110. So you can go down, but what he told me recently is that he's done a lot of work on his laser locks.